A rigorous causal question doesn't ask if two things are merely associated. It asks what happens to the exact same unit under two alternative interventions. Under the Rubin causal model, a unit has a potential outcome under treatment, labeled y sub I of 1, and under control, y sub I of 0. We calculate the individual effect by subtracting control from treatment. True causal logic forces us to think in counterfactuals. We have to compare the reality that actually happened against a parallel reality that did not. But here we hit a physical wall. The moment a patient takes a pill, the control state ceases to exist. Paul Holland formalized this impossibility as the fundamental problem of causal inference. Because one potential outcome is always missing, the true individual causal effect is completely unobservable. We can never be certain what caused a specific result for a specific person. To escape this problem, we have to abandon the individual entirely. A randomized controlled trial steps away from the single unit and uses a physical mechanism to solve the missing data problem at the population level. Take a large population. Every unit inside it holds vast hidden complexities: genetics, income, daily habits, environmental exposures. When pushed through a random assignment mechanism, the population shuffles into a treatment group and a control group. By pure chance, hidden complexities mirror each other across the divide. We call this exchangeability. Random assignment makes treatment independent of potential outcomes. This means we don't need to measure every single baseline cause of an outcome. The random draw neutralizes the unmeasured variables, making the two groups highly comparable. Randomization is a physical, mathematical engine. It constructs the exact conditions we need to isolate and identify the average causal effect. In causal inference, we have to separate identification from estimation. Identification is proving that the causal quantity we want is uniquely determined by our data and our assumptions. It asks, is this effect theoretically measurable? Estimation is the mechanical process of crunching the numbers to learn that quantity from a finite, noisy sample. No advanced estimator, like flexible regression, complex matching, or a machine learning algorithm, can magically repair a failure of identification. If the underlying logic is flawed, adding more processing power only gives you a highly precise, entirely wrong answer. The true advantage of a randomized controlled trial is transparent identification. It gives us a known mechanism to trust before we ever run a calculation. But randomization only protects the baseline conditions before the trial begins. The moment an experiment relies on human behavior, choices intervene and reintroduce confounding. We can see this clearly in the Oregon health insurance experiment. Oregon didn't force Medicaid on a random set of people. They ran a lottery, an encouragement design, assigning the opportunity to apply. These post-randomization choices broke the clean experimental lines. Some winners never enrolled, and some losers eventually found coverage elsewhere. If we compare people based strictly on whether they won the lottery, we get the intention to treat, or ITT, effect. This preserves the perfect randomized contrast, but it measures the effect of being offered insurance, not the biological effect of receiving medical care. To find the effect of actual coverage, we use the lottery as an instrumental variable. The Wald estimator divides the numerator's ITT effect by the denominator's compliance rate, isolating the local average treatment effect for those whose enrollment behavior changed. Because human reality defies perfect protocols, applied researchers cannot simply report an average effect. They must rigorously specify which divergent causal contrast they are actually estimating. Standard randomized trials rely on a hidden pillar called the stable unit treatment value assumption. This requires that one unit's outcome depends only on that unit's treatment, isolated from everyone else. That assumption collapses completely in studies like the Bangladesh community masking trial. With infectious diseases in dense social networks, complete isolation is simply implausible. If giving person A a mask lowers their neighbor's infection probability, standard comparisons fail. The control group receives a passive treatment dose. The solution is cluster randomization, assigning entire villages to treatment or control to trap spillovers inside the randomized unit. When social or biological spillovers are present, contamination is not a statistical nuisance to be ignored. It is a critical part of the causal effect that policymakers actually need to measure. While random assignment provides incredibly transparent identification, the evidential force of a trial is fragile. It depends entirely on physical execution, strict allocation concealment, high adherence, and complete follow-up. Then there is the problem of transportability. A flawlessly executed trial in a specific historical context does not mechanically generalize to the future. The 1948 British trial of streptomycin for tuberculosis established prospective experimental methods in medicine, but its specific causal estimates are effectively useless for modern patients because monotherapy rapidly selects for resistant organisms, and today's treatment systems require multi-drug regimens. Declaring an RCT the absolute gold standard limits our thinking. A trial is only as credible as its strict boundary conditions and its real-world execution. When random assignment is unethical, too slow, or physically impossible, causal inference does not end. Researchers instead construct alternative, defensible sources of exchangeability using observational data. This creates a continuum of quasi-experimental designs, each relying on a specific identification argument tied to how the data was generated in the real world. A difference in differences design demands parallel, untreated trends over time. A regression discontinuity exploits strict administrative cutoffs where treatment jumps discontinuously. The movement known as the credibility revolution demands that researchers explicitly state what variation identifies an effect and rigorously justify the assumptions connecting observed data to counterfactuals. The highest standard of evidence is not a study label, it is the uncompromising clarity of the causal argument.